So today I wanted to talk a little bit about systemd and some of the history that led up to its use. What are we talking about here? What is systemd? And more importantly, what does systemd actually do? So I'm going to back up, as I always do, and talk about what came previously. I'm not going to talk about Unix so much, even though Unix played a part in the early days of how Linux worked. I don't feel like it's really all that important for this discussion. So let's talk about what do we have in the sequence of order. If you remember when I was talking about in a previous video about the steps that Linux takes in order to bring your system up, we have what's called a boot sequence that begins the whole process after you hit the power on button, of course. It is during this phase that your BIOS or UEFI locates and executes the bootloader, or the UEFI can load the kernel directory. So what's the bootloader? The bootloader can be grub2, can be lilo, it can be refined, and there is a systemd process that can be used here as well. It was, I think, called Pixie Boot at one time, and then it was incorporated into the systemd family of system products. So anyway, once we have the kernel loaded into memory, the kernel goes through its initialization steps and discovery and all that. But one of the things that it does is it starts up what's called the init process. That's otherwise known as process ID = 1 or PID1. So this init process ranges in system initialization steps. So it can either be systemd, it can be sys5 init, it can be openRC, it can be Upstart. There's a number. There's probably a list that's probably 14 or so deep of applications which can serve as the init process. But the init process is really meant to manage the housekeeping functions of the system and start up various services that are needed by that machine. And once it has completed its initial target or its initial run through, it then hands over control to the login shell or to the display manager process at that point, depending upon what your system is doing. So if it's a server, it goes through the login process or whatever. So the init process is the first user level process that runs on a system. It will continue to run until you shut it down. Until you shut your system down, that process will always be there. Now, if some reason that it fails, the kernel will restart it. So it will restart it again so it continues to run. It is usually, whatever this process is, it's usually symlinked to /sbin/init. And then that is what the kernel uses, of course, to start, because the kernel doesn't know which init process you're running. All it knows is what it is directed to do in the code. So the init process has four basic functions that it does. So we talked a little bit about housekeeping, but there's really four different things that it needs to do. So the first thing is it handles the later stages of the boot process. Now, what do we mean by that? Well, I may have to mount file systems. I might need to do specific device discovery, or I might receive messages from devices that need to be handled, such as if I have drives that are on a USB or a Thunderbolt partition, for example. Also, it configures the environment. So I'm talking about the system environment, not your login shell environment. This is the one outside of yours that all of the processes will inherit from. So yeah, specific path variables, specific things about the runtime that those processes need to be aware of. The third thing that it does is it then starts all the processes that are needed for logging into the system. It also works with the kernel to clean up after processes that are terminated. Now, prior to systemd, the init process would inherit orphaned processes. That is, so there in Unix terminology, there are two types of processes that can occur. First is the orphan process. The orphan process occurs when if you have a parent-child, that is, a parent process forks a copy of itself, and then the orphan process then launches or execs a different application to substitute for the one that forked. But they are interrelated. The parent and the child processes remain to be interrelated. An orphan process occurs if the parent process dies and the child process continues to run. It's called an orphan process. And so in the pre-system D days, the init or PID equal 1 process would then inherit or become the parent process for that orphan. And the first thing it would attempt to do would be to try and shut it down, shut the orphan process down. And today that is using kthread D, and that is started by the kernel. So yeah, it no longer gets inherited. Kthread D, if it spots an orphan process, it'll immediately try to shut it down. Meaning, because it assumes that there was a relationship between the parent and the child, and unless you handle the interrupts you can override it in code, but generally it's going to fire an interrupt at you that on the orphan process to terminate. So, yeah, it doesn't mean you can't thwart it. You certainly can. In Unix we had something called a zombie process as well. What does that mean? So, because of the way that Unix worked, if your child process terminated for some reason, it blew up, or it reached a condition where it needed to stop, maybe it ran out of resources or some other reason, but it terminates, and the system hasn't yet identified that system has gone away, and the process table still contains an entry for it, even though there is nothing there. So that becomes a zombie process because there's a process ID that's saying it's active, but there is nothing in memory that's actually running. So a zombie process would branch to something in the kernel called a zombie walker, which would then go down through the list of the process table and ensure there was a matching process that was running. If there wasn't, then it would remove the entry from the process table, and it would be referred to as that process had been reaped. And that was the way Unix handled those kinds of situations. The oldest PID process in Linux was called originally sys5init. So it was an attempt to mimic what the original initd process did under Unix System 5. So Unix System 5 didn't call it System 5 init, it just called it init. But it started up as a system process and used a serial method of execution. That is, it could not launch different services in parallel. It could only do them one at a time. sys5init was not very smart. It didn't know about dependencies. It didn't know about conflicts. It wasn't a package manager, so it didn't know all these things. And so it assumed that, by convention, we'll go through that. But there's a convention that you use to manage what gets launched first. But SysVinit organized its runtime environment into a sequential set of stages. And each of those stages had to complete before the next one could begin. So, you basically had a pretty long startup time on most of those early systems because of the way in which it worked. So, each stage to System 5 init is known as a run level. So what run levels did sysinit v define? Well, there's a number of them. So the first one was run level 0, which was that identified the system in a halt state. So if you had issued a halt command to the system, the first thing that would happen is the init process would begin executing anything in the run level 0. So, and that would be, of course, to shut down everything in a graceful way and then halt the system. So the second one was single user mode, which means no other users could log into the system. The only person allowed on was the person at dev console. So in the early days. And so the single user mode is identified as either run level 1. You might see it as a run level capital S or run level lowercase s. They all mean the same thing. There's also run level 2, which is multiple user. Now, these are conventions. 2, 3, and 4, and 5 are all done by convention. There is no right or wrong in the way they're configured, and you will find differences from one distribution to another on how they're implemented. But the general rule was, and this comes from Unix, the general rule was system level 2 was multiple user, but no NFS, no networking, and only provided a text login. So this would be a system that used terminals probably or modems to have multiple user support. But it didn't have graphical displays. It didn't have any kind of networking. So, right. The third type was multi-user level 3, level 3, which would allow for multiple users. That allowed for NFS. It turned on networking, but it still maintained a text login for the base system, so it didn't bring up a GUI or anything like that. Level 4 was never used. However, I used to use it for custom testing of the kernels. So when I was working on Unix, I would use that pretty much for any kind of custom testing that I was doing. The level 5, but again, it isn't declared as to how you can use it. Level 5 is multi-user with NFS, networking, and a GUI. So that means either Wayland or X11 is launched on those systems. Finally, we come to run level 6, which indicates a reboot. So it would go through a sequence that would, again, mimic the halt state. It would begin to shut down processes. And once everything was done, rather than bring the power off command into play, it would do a system reboot, which would restart the system. So, yeah, and you'll find, a lot of variation between these. There are also ways with sys5 init to dynamically change the run level even after you've already booted up the system. There are 2 ways to do it. You can execute the run level command using a capital N and then a number, and the number is the run level that you want to execute or to launch. The other way is to use telint, and telint also has to be run as sudo, and it's an sbin, and then you follow it with the run level that you want, and that also will restart the system. The reason for those 2 have to do with history and the number of changes that were on different systems at the time. But those are inherited from the Unix community. So basically, how does SysVinit work? So it works something along like this. I mean, there's a lot more to this, but I'm just going to simplify it. So the first thing that sys5 init does is it reads etc init tab. And originally, that would direct the system init process to run scripts to begin starting up the run levels. So normally what would happen is it would run a script called rc.sysinit, and that would run with run level being passed as an argument. So if it was run level 5, it would pass 5 to the rc sysinit script, and then the sysinit script would then in turn run each script in each of the directories that it was directed to by the run level. So what directories did it go to? Usually it was /etc/rc.d, and then under there you'll find directories for rc0, rc6, and so forth. So rc0 through rc6. You may also see some that are for the shutdown and so forth that are in there as well. But each script is prefixed underneath that directory with a number, and that was convention. So you'll see usually it's an S for start and then a number, and a K for kill and then a number. So depending upon which operation that the system was executing, whether it was trying to bring down the services, it would look for ones that begin with the letter K. If it was starting up, it would look for scripts that began with S. And then it would start executing those in order. Now that's just convention. There is no rules about how the numbers are specified other than the fact that that orders them in the directory. And so the script is just going to read them in alphabetical order in the directory, and that's all there is to it. It is not a hard and fast rule that you can't have. Well, first, you can have more than one K00 because you might be using that to group together services that run under, or in the K version, you may be shutting down a group of services all at once. Or you might see S00 with, you might see SSHD, or you might find another one that maybe was bringing up the clock or something like that, where all these services were starting up together. That was an attempt to do parallelization. Of course, it didn't run in parallel because it still had to go in and individually run each script. But it was an attempt to actually group them is all it was trying to do. So System v Init was really designed ordinarily for very large mainframes with many logged in users, and those users typically were logged in through serial terminal devices. And they ran continuously. They were rarely rebooted. So System 5 and Init was not designed for the dynamic environments that we have today, and and heavily networked and environments that we have with virtualization and containerization, where we're constantly shuffling things around in the environment in order to load balance across all of the servers. So Sys5 Init was just never designed for that kind of workload. So because of some of the problems in System 5's inherency in doing serial execution, which of course slowed down the startup, there was a lot of alternatives that started to appear, and one of them was openRC. Then came Upstart, and then finally System D. So we'll talk about each of those kind of in turn. But as those alternatives began to appear, openRC was developed in, I think, 2007. It's currently used by Alpine Linux, Funtoo, Gentoo, and Nitrux. So you'll find that is the preferred init process. Now, openRC does have parallelization. And I'm going to direct you to, there's a Gentoo page, I'll put a link below, that lays out all of the init processes that are available on Linux. It goes through their pros and cons and the various features that each of them offer. The next one that came about after openRC was Upstart, and Upstart was developed by Canonical, and it was initially adopted by Fedora and implemented as, I think it was default in Fedora 9 and also in Red Hat Enterprise Linux 6. So, but a Red Hat system developer by the name of Leonard Pottering had looked at Upstart and was a little bit concerned that Upstart had some features that were missing. And he also didn't like the way it was architected. There was some issues with it that he felt were going to cause problems down the road. So he started working with another guy from, I forget, his first name was K, but I don't remember his last name. But those two together began working on System D. And Fedora adopted System D in 2011. RHEL 7 adopted System D. And Ubuntu started using System D with 1604. And Debian, the long-term holdout attempt, they went to it in 2012, just a year later. So there are a number of releases of Linux. There are a few anyway, that do not use systemd, Devuan being one of those, Alpine, of course, being another one. There's also some of them that can be changed out. But, you know, the thing is that you have to realize that if you do go backwards and you are mixing packages from different sources, you may run into issues because the world has moved to systemd. So unless you are pulling your packages directly from your Linux distro's repository, it is possible that those services just will not run. And the reason they won't run is they're looking for systemd constructs in order to launch. So let's talk about systemd a little bit. So what is it? Well, it's a system service that runs as PID1, and it defines services as units. So unlike one of the main issues with System 5 Init was it could not separate out different services. It was either you started them all up under run level 3 or you didn't. So yeah, you could not say, oh well, just launch this group of services but not these. But so the systemd defines each one of those services as a unit. And those units can be run with dependencies, or you can declare conflicts with other units so that those don't come up and occupy, for example, the same socket number or something like that would cause a conflict in your system. So units are only started after the depends. So in the declaration for the systemd configuration, and in there you specify the services that yours is dependent upon. If you need a system clock to be set, you may set it to one of the NNTP services, or if you had DNS was an important part, you might have bind or some other service that you're dependent upon that needs to be started before yours. So each unit is configured via text file instead of a shell script. Now System 5 Init uses shell scripts to actually start and stop the processes. There's also some in there that will record, that you take the status and will return the status of what the service is doing. The other thing that systemd does is it replaces those run levels with what it calls targets. And targets is how you group together the units to define specific system states. So once all the requested units have been started or stopped, that target is then fulfilled, and systemd will stop attempting to try to launch system units. So it has, there are definitions that equate back to the run levels. So systemd defines the following. So it calls rescue target. That roughly is run level 1. And then you have, that would be the single user. And then you have multi-user targets like that would be similar to run level 3. You have graphical.target, which is run level 5. Power off target would be similar to run level 0. And reboot target would be similar to run level 6. There are many, many more targets that are defined in systemd. I did not go into them. For example, one might be the Bluetooth target, and that one gets called as soon as systemd recognizes that there is a Bluetooth device that has started up on the system. So it is responding to events, and that is a clear delineator between systemd and any of the others, is that systemd can respond not only to a particular order in which the system administrator desires these things to come up, but it can also respond dynamically to changes in the system environment that it needs to respond to right away. So that's an important differentiation between all of them. So some of the pros of systemd is that it is a faster boot process. It's more flexible to adapt to new situations because of the way it's architected. It has a standardization of configuration files, whereas some of the configuration files under System 5 Init, and I can attest to this, you would find differences sometimes, and sometimes those differences would be would be so radical. It'd be like, what are you doing? That they would not adhere to a particular way of doing things. Oracle being one of those. Oh, sorry, I didn't mean to say that. Simple interfaces for end users to interact with. And then there was other fancy additional features that extend its capabilities out. I think I remember reading on Pottering's blog that if you fully configure systemd, you will get 69 processes defined as part of the end result of your compile. So, yeah, it can do quite a bit. Some of the cons, well, I mean, the major one I've always heard is feature creep and bloat. That systemd is really starting to it is starting to invade upon traditional environments that the kernel would have had authority over. So and there's some concern about that from the standpoint of security because systemd does run as a user process. Now, systemd attempts to limit its view of the system by not running as root. However, that's pretty much left up to the distro. So you could find a distro that is incorrectly configuring systemd to run as root. So yeah, and that would be bad. So the other thing is, I think it's kind of interesting that I've heard a couple of people talk about the Unix philosophy and that systemd violates the principle of do one thing and do one thing well. Again, if you go back and you look at my video on Unix philosophy, that actually wasn't the point of the Unix philosophy. That was an add-on that came later. But that one, the logs stored in binary format, that is a violation of the Unix philosophy because Unix philosophy wants all files to be in text. That way they can be piped to other processes and you can reformat them. So that is a bad thing. And I would disagree with Pottering on having that in there. That is wrong. And that limits the ability of systemd to be integrated with other applications. So the other one is interlocking dependencies. We refer to that in the architecture world as being tightly coupled. That is undesirable. In architectures that are built to be flexible, we prefer things to be loosely coupled in order that we don't have hard APIs that we have to adhere to. Those are generally areas where systems can break. It's hard to avoid systemd and to replace it or use it in part because it's an all or nothing strategy. Again, that goes back to its tightly coupled nature, and so that's really part of the interlocking dependencies, in my opinion. You may disagree with that, and that's fine, but I've been an architect for a long time, and those are things that we have always tried to avoid because history has shown us that those are things that will come back and bite us later, and they will cost us millions to fix. Singular design mission based on Linux and won't easily port to BSD. That may not be a big deal to you, but what if down the road Linux goes under and we are going to try to use systemd for some other system? It means it would have to be rewritten. So again, tightly coupled to the operating system, same issue. So yeah, there are other issues that are non-technical that have been slated with systemd. One is leadership issues, particularly with the systemd development team being totally unresponsive to users' fears and doubts about the system. The other one is there are ongoing support and security concerns. The system has grown so large that the concern is what happens if the development team decides to move on. And in fact, Leonard Pottering has moved on. He's moved on from Red Hat to Microsoft. So his direction now is going to be set by a company outside of the Linux sphere, and they may not be. So I know he's working on systemd still, he says, but that may change over time. So those concerns are still valid. So those are, I mean, I can go deeper into systemd. We can talk about how to set up things like how to set up these various things, like how to set up your own target. You can do that. You can set up your own unit. You can do that. You can set up your own configurations. But there are manuals. Some of the best manuals on systemd are out in Red Hat in their repository. So if you're interested in reading deeper into the systemd topic, I'll give you some links below today, and then you can go out and check those out for yourself. But that's all I had for today. I hope you enjoyed this, look at some of the history around the PID equal 1 process and what it's for, how it works, why it was developed, and some of its shortfalls in its early designs, because Unix, it was never really developed with networking in mind. In fact, it didn't have networking even available to it in its early days. It didn't have graphical user interfaces as part of its design either. That's why everything is bolted on to the outside of even Linux. So anyway, that's all I had. Hope you enjoyed this video. If you did, as always, please like and subscribe. Hope to see you all again real soon. And bye for now.